When you run an electric current through a thin layer of hydrogen gas inside a glass tube, it begins to glow. Usually, if you shine light through a prism, it spreads out into a smooth, continuous rainbow. But if you pass that glowing hydrogen light through the same prism, the result is completely different. The prism splits the hydrogen light into distinct, isolated bands of bright color against a pitch-black background, an emission line spectrum. Compared to a full continuous spectrum, the hydrogen spectrum appears almost completely empty. Vast stretches of color are simply missing. Why does hydrogen exclusively emit these few specific wavelengths of light while completely ignoring the rest of the spectrum? This macroscopic barcode of light functions as a readable signature of the hidden microscopic architecture within the hydrogen atom. In 1913, Niels Bohr suggested that electrons don't spiral freely around a nucleus. Instead, they orbit in fixed quantized energy levels. We can visualize these allowed states as a ladder. At the bottom is the lowest energy state, the ground state, labeled n equals 1. Above it sit higher excited states, n equals 2, n equals 3, and so on. Imagine an electron that has temporarily acquired energy from an electrical current. It now sits high up on this ladder, for instance on the third rung, in an unstable, excited state. Because the atom seeks stability, the electron can't stay up there forever. It spontaneously plummets down to a lower energy state. Bohr's third postulate states that the exact difference in energy between that initial high state and the final low state must be expelled from the atom as a single photon of light. Since the rungs of this ladder are rigidly fixed, the distances an electron can fall are also fixed. This guarantees that the atom will only ever emit specific, discrete colors of light. Now consider the opposite scenario. What happens if you take a continuous spectrum of white light and pass it through a cloud of cold, unexcited hydrogen gas? Returning to our energy level diagram, we start with the electron at its baseline, the lowest possible energy rung. A wave containing every color of light is heading straight for it. Most of those incoming colors possess amounts of energy that don't precisely match the gaps between the rungs. Since the electron cannot jump to an empty space between rungs, it ignores those photons and they pass right on through the atom. However, if a photon arrives carrying the precise amount of energy required to bridge the gap to the next level, the atom consumes it. The photon vanishes and the electron instantly jumps up to the higher rung. This stealing of a specific photon is called absorption. Because that exact packet of light never makes it through the gas cloud, a permanent gap remains in the transmitted light. By consuming only the exact frequency needed to climb its internal ladder, the atom leaves behind a distinct dark line, creating the absorption spectrum. This visualization compares the two phenomena directly. The top bar is the hydrogen emission spectrum. The bottom is the absorption spectrum. When stacked, the bright emitted colors and dark absorbed gaps perfectly align at the exact same frequencies. This is because the energy required to jump up a specific step is identical to the energy released when falling down that same step. The atom pulls specific light in to climb up the ladder, and it pushes that exact light out to fall back down. These spectral lines act as a literal map of the hydrogen atom's internal limits. The quantum rules are strict. If a mathematical distance between two energy states does not exist within the atom, that corresponding color will never appear in its spectrum. Hydrogen's two-way street of emission and absorption provides visual proof of quantized energy. By observing the light an atom accepts and rejects, we can map out the invisible architecture of matter.